Okay, in this podcast, we're going to talk about what happens when we have concentrations of our solutions that are in the battery that are not 1 molar. Because up to now, what we're talking about is non-standard conditions. If you remember, the values in the standard reduction potential table is E naught NaUGHT, which means standard conditions, which suggests 25 degrees C, but it also says that the concentration of the solutions, of the metal ion solutions, are at 1 molar. So a lot of times we don't have solutions that are at 1 molar. It might be at 2 molar or 1.5 or 0.1. So we need to think about what's going to happen when that occurs. And before we can talk about how to determine what happens, we need to talk about equilibrium and what happens when concentrations change. Okay, so let's get started. So if we think about reactants and products, when we've talked about this in honors chem, we generally write the equation like this. We have reactants and they break bonds and form new bonds and we form products. But in fact, what really happens is we also have products, once they're produced, that go in reverse and make reactants. Okay, and it's a dynamic process. So for instance, you might have this reaction between hydrogen and iodine where you're forming hydroiodic acid, and the larger arrow suggests that the products are favored here, but there is a little bit of reaction going backwards. Okay, that there is some HI going back and becoming H2 and I2. You might have other reactions. For instance, this is a famous reaction. It's called the Haber process for making ammonia, where you have nitrogen gas and hydrogen gas that make ammonia gas. And this reaction favors the reactants. So you have more product turning into reactants than you have reactants turning into products. And eventually, once you have the materials in the reaction vessel, you will reach what's called equilibrium. Okay, and equilibrium is when the rates of the forward and the reverse are the same. So let's say I start with a reaction and I have reactants up here, right? I have a large amount of reactants, and their concentration declines as the reaction goes forward. Reactants, the products, I start off with no product, and as products get produced, they eventually start to go and become reactants. And when the rate of the forward and the reverse reaction are the same, when this point hits, we say the reaction is at equilibrium. It doesn't mean the reaction has stopped, that there's no reactants making products and no products going back into reactants. It just means that the rate of the two is the same. And if you hit this point in a battery, when you hit equilibrium, when E is zero and the battery is dead. Okay? The battery is dead. Okay. So we can do things, and it was really important in the case of the Haber process when you're taking hydrogen and ammonia and making hydrogen and nitrogen and making ammonia, that you are able to cause a shift towards. Remember that the reactants were favored. There are things you can do to try to shift this reaction to make more product, and that was really important because the development of ammonia stopped world hunger because ammonia, as you probably know, is used as a fertilizer, and the ability to produce it in large quantities is what changed the war in World War II, and it also led to the elimination of a lot of poverty. So it's a really important reaction. It remains an important reaction, and trying to get more product is really important. Okay, so we'll talk about the Haber process a lot. But Le Chatelier's principle is one of the things that is used to help us have a more effective or a greater yield in our ammonia production and in a lot of reactions. And what it says that if a chemical system at equilibrium, which means the forward and the reverse are the same rate, right? We drew that graph that shows the forward and the reverse rate are the same. I apologize for my drawing. And then there is some change in that equilibrium for concentration, temperature, volume, or pressure. Then the equilibrium shifts to counteract whatever the change caused. So let's take a look at what that means. Well, in terms of a battery, my eraser is working. Okay, in terms of a battery, what that means is if I increase the concentration of a reactant, let's say a metal ion, that will favor the forward reaction, and that cell potential E will go up. Okay? On the other hand, the reverse is also true. So if I go increase the concentration of the metal ion and the electrons were flowing this way, right? And I increase the concentration of this, it's going to shift it back. Alright, so let's take a look at a specific problem where we can start to use this. And here's just a little pictorial of Le Chatelier's principle. So let's say we have this system. This is the Haber process, again, for making ammonia, where we have nitrogen and hydrogen on the reactants, and we have ammonia and heat being produced. Okay? And there is a certain equilibrium at which these guys are balanced, and they are the amount of reactants and products is relatively the same. The reaction continues to go back and forth, but they are balanced. If you add more reactants, okay, that's going to increase the concentration over here. And what Le Chatelier says, we want to shift the reaction to get rid of the excess here, and that is going to cause us to produce more product. Okay, so what that says, if we want to make more ammonia, all we have to do is increase beyond the regular stoichiometric amount of ammonia and hydrogen, and that will shift the reaction to the right, meaning I get more product. Okay, so this is what we can do in a battery. We can shift the side that is undergoing oxidation to cause a higher voltage. Alright, so here we have a reaction. We have a cell, we have aluminum, and we have manganese, and they are undergoing oxidation and reduction. And it tells us that the aluminum is going from aluminum to aluminum plus 3, and the manganese going from plus 2 to 0. So let's start with the manganese. I have 3 manganese, 2 plus, becoming 3 manganese, 0. So I must be gaining 6 electrons here. Okay, and I have my 2. Now, the equation that is here is 2 aluminum becoming 2 aluminum 3 plus I'll need 6 electrons here. Now, if I look at the table, the standard reduction potential table, I'll put my hands on it, it says that the Mn plus 2 going to manganese is minus 1.18, and that if I have aluminum, now if I have aluminum plus 3, what the table says is aluminum plus 3 electrons gives me aluminum solid, and that would give me a E volts of E 1.66 volts. Okay, but because I have shifted the reaction around, this is going to be a positive 1.66 volts because the aluminum is undergoing oxidation and not reduction. So my E cell is going to be I add these together, it's be 1.66 volts minus 1.18 volts. And when we do that, go ahead and punch it with me. I get 1.66 minus 1.18, which gives me 0.48 volts. Okay, that's a little practice using the table. Okay, So now it says, let's take a look at A. Predict what will happen with E cell, which is not, it doesn't have the not, so this is not at standard conditions. It's no longer 1 molar or 1 molar, is larger or smaller than the E cell following the case. Okay, if we think about what we have the aluminum, which is undergoing oxidation, right? We have our salt bridge, right? So let's say we have the aluminum that has an Al plus 3. I have aluminum here. My electrons are going this way. And I have manganese here and manganese plus 2. Okay. So what's going to happen is I have electrons that are leaving here, leaving the aluminum and going over to the manganese. Okay. So if I take this Al plus 3 and I increase the concentration so I have 2 molar instead, and I have 1 molar of the manganese, 1 molar of the manganese plus 2. So what's going to happen here? So if I think about it, what I'm trying to do is I am producing plus 3, right? The aluminum is losing electrons, becoming plus 3. So these are my products. These are my reactants. So my product is, I'm just going to write it above here. This is for sample A or question A, 2 molar, and my manganese is a 1.0 molar, right? So I have a higher concentration than E naught on my product side, and what Le Chatelier said is that that is going to cause a shift towards the left or towards the reactants. So when I do that, it's going to cause this reaction to shift left, okay? And as a result, my E cell will be less than my E naught cell, okay? So by increasing the concentration of aluminum ions, which show up as the product, I'm going to have a lower concentration. Okay, so let's take a look at the other example. And I'm just going to erase this here, make a little bit room for B. So B says that aluminum is 1.0 molar and that my manganese is 3.0 molar. Well, here I have a standard concentration of the product, and I am increasing my concentration of my reactant. So what that is going to do is shift this reaction to the right, away from the higher concentration here, which is going to cause me to have more oxidation, more reduction, and therefore a higher E cell. So for A, I got a lower E cell. For B, E cell that's not at standard conditions, at the condition listed in B, is going to be greater than E naught cell. Okay, in the next podcast, we're going to talk about how we actually go ahead and quantify that.